So hi, everybody. Welcome. I'm really glad to present the thesis defense of Zachary Gregory. He's going to be talking about artificial intelligence and mesophotic reefs. Zach comes to us from Mukilteo, Washington, which is a cool little town on the Puget Sound. And he did his undergraduate degree at Western Washington University. Go Vikings. And then came to us in the 2021 cohort. He had a really cool project all set up to do to use robots to map these deep coral reefs, and the robots didn't work. But so he developed a really cool project about using artificial intelligence to identify corals from imagery taken from many different projects. So Zach, when you're ready, please take it away. Thank you.
Yeah, all right. Thanks, Tyler. So like Tyler said, I'm doing my thesis on artificial intelligence and mesophotic reefs, how AI image identification can aid our understanding of deep coral distributions. To start us off, should probably talk about what mesophotic reefs are. Typically, when we think of coral reefs, we're thinking of something like shallow water reefs, which are coral ecosystems that occur typically above about 30 meters depth. Mesophotic reefs are very similar. They have a lot of the same species. The only difference is the depth distribution, which causes a lot of difficulties with light availability for these corals. So mesophotic reefs typically occur between about 30 to 100 meters is their sort of agreed upon depth distribution. Most these corals can survive typically down to about 90 meters in the Caribbean. However, in some other places, they can get deeper than that. What's really interesting about these reefs is they haven't really gotten a lot of research when compared to shallow water reefs. This is due to a number of things, but the primary reason is that they're just harder to research. At this depth, the techniques you would typically use are either a lot more inefficient, something like having to do drop cameras, dropping basically a camera on a rope off the side of a boat to get images of the benthos, or tech diver surveys, which require a lot more specialized training, expensive equipment, and those sorts of things. These ecosystems are, their community composition is driven by their depth distributions, usually by that light availability. So in the shallow water, the shallower mesophotic reefs, you'll have different community compositions than at depth. And around St. Thomas, around the Virgin Islands specifically, Orbicella and Agaricea tend to be the two dominant reef building genuses at depth. So speaking about their distributions, we usually think of this in sort of two capacities. There's their vertical distribution along that depth gradient, and then there's the horizontal distribution sort of across their like latitude and longitudinal positions. Looking at the vertical depth distributions, like I said before, we have shallow water reefs above that 30-meter mark. We have the upper Mesophotic, which stretches between about 30 to 45-ish meters. The mid Mesophotic goes a little bit deeper, around 45 to 60 meters, and the lower Mesophotic is 60 to 100 meters. Typically, looking at this upper Mesophotic area, this is where you're going to see more of those orbicellid species tends to dominate that upper area where light is more available. Then in the mid-Mesophotic, you start to see a community transition from orbicelids to Agaricea species, which are a little more tolerant to low light conditions. Then once you get to the low Mesophotic, you start to see a transition from Agaricea to things that are a lot more tolerant of a very minimal light environment, something like sponges or things like that. And the vertical depth distribution, at least in the Caribbean, is very well studied. We have a pretty good, at least comparatively, pretty good understanding of what are the factors causing these distributions. Horizontal, on the other hand, has a lot less research to it. What we do know is from some literature along St. Thomas, slope and aspect, which is the direction the slope is facing, north, south, east, or west, can have impacts on community composition and coral cover along the Puerto Rican shelf edge. Reefs north of St. Thomas tend to have lower coral cover than those south of St. Thomas. Groves et al. 2016 attributed this to higher wave energy north of St. Thomas, causing more mechanical disturbance in these reef environments. And then a study in Hawaii that was looking at similar uh, distribution along geomorphological terms found that their slope of slope, or the derivative of the slope, distance from the nearest landmass, sea surface temperature, and euphotic depth were all predictors of one or multiple mesophotic coral species in Hawaii. Looking specifically at the geomorphology that's interesting around St. Thomas, there's the one big geomorphological feature that gets a lot of attention is the shelf edge. So there's a trench, the Puerto Rican trench, that runs south of St. Thomas, and it has this really geomorphologically complex shelf edge that covers the Mesophotic area right before you get into the trench. It has, if you look at this graph right here, we have these shallower or these flatter areas like terraces and buttresses, and then there's more sloped areas. So it's this really complex uh, area that provides a lot of potential places for corals to be able to um, inhabit. And because it's so complex and because it has higher levels of coral typically, there's a lot of research that happens along the shelf edge. Most of the research from mesophotic corals around St. Thomas typically occurs along this shelf edge because corals there are more available and more ready to be studied. Um, that leaves the rest of the mesophotic zone a little less studied than the shelf edge. So understanding how these geomorphological characteristics affect the rest of the mesophotic area is going to be one of the things we're focusing on today. So talked a lot about there's not a lot of research out there, and where we have done research, we've really had to focus on areas where we think we're going to find interesting things. That's because of these challenges that I alluded to earlier, these data collection problems that the Mesophotic has with either inefficient or expensive um, techniques to study them. However, in recent years, we've actually had a lot of technologies start coming out that are starting to make researching the Mesophotic area a lot more accessible. So there's new developments in underwater cameras, in not diving techniques, sorry, in ROV and AUV technology. For example, the Ranger bot that I have right here that I was using for the original project. And this is starting to cause an influx of images of the Mesophotic, uh, which is great for research because it gives us so much more data to process. However, the advancements in processing this data hasn't caught up with this sort of revolution in being able to get this data. So typically what we've been doing at UVI with our Mesophotic data sets is we've been doing dot analyses where we put a bunch of dots on an image and identify everything by hand at those dots, which means with this influx of data, it's hard to have a scientist spend all of their time going image by image. So we have a problem of how do we start analyzing all of this data? And one potential avenue that has gotten a lot of attention is computer vision. So computer vision is a essentially field of science that was invented by Hubel and Wiesel in the 1950s, but it really got a jump start in 1979 when neural networks were invented by Dr. Fukushima. Um, these are basically self-learning networks that you can have a computer start to teach itself. They're based on the way our neurons communicate with each other. Um, and this is how most of the self-learning AI that we know today has been built upon neural network frameworks, which has caused, as a lot of us know, a lot more accessibility in AI in recent years. And that has worked its way into marine science. So AI has started to be become used across pretty much every branch of science. Specifically for marine science, we have seen it used for benthic image analysis, which is what I'm going to be using it for today, for analyzing what the benthos is made up of. And a lot of reef restoration places have used it for reef monitoring and restoration efforts, so tracking things like coral spawning, coral diseases. It's been really good for a lot of those sorts of projects. However, with this sort of revolution in using this technology and it becoming so accessible to so many people, we haven't taken the time to really standardize a lot of techniques for either how we train these models or how we communicate the structure and framework for how we built these models up. So having that sort of foundational understanding of how to standardize these things, how to build these models for the scientific community is going to be really important going forward, specifically for mesophotic corals as well, because mesophotic corals run into a lot of unique problems. One thing to note is that while I did mention there are a lot of shallow water coral models out there that identify corals in shallow water environments, they typically can't be used for mesophotics because of that low light availability. Causes mesophotics to take a plating morphology, to take a different morphological shape than you see in shallow water, which is going to be something that the model isn't trained on and isn't going to be able to really jump from shallow water to mesophotics. Which leads to the challenges that we're going to face in training a mesophotic AI image identification model. So the biggest one is going to be quality and quantity of training images. When you're training a model like this, you need a lot of annotations, typically 1,000 annotations per class that you're trying to train on is what's typically accepted. So that leads to a problem with mesophotics where we don't have those big image sets typically that you would see in something like shallow water reefs. There's also the problem of generalization. AI models are not really good at generalizing to conditions that they haven't seen before. This is why we'd have problems using shallow water models on mesophotic corals. So if you have changes in light condition or turbidity, these are going to be things that are going to mess with the model's ability to identify what you're interested in. And when you look at the mesophotic, we run into a lot of issues like that, where we can have two images with drastically different color states and light conditions. We have, like you'd see in this image here, we could have something like flashlights changing the way shadows work and color saturation. Have a blue shifted image here where it doesn't have that flashlight, but it's still deeper and has those problems with light availability and color changes with depth. So that's all going to affect our how difficult it is to create this model. The last thing we run into is the annotation accuracy for the scientist building your model. Your model is only as good as the person training it. So if a person is training it and identifying corals incorrectly, your model is going to identify corals incorrectly, which again runs into a unique issue in the mesophotic, where a lot of the corals, you can't identify species to species just on the images. So to solve that for this project, we decided to focus just on the two genuses and really try to hone in on those two. So the purpose of our study is kind of twofold. We have our first objective, which is to develop this AI identification model. And we want to start to chip away at that standardization of techniques, see what works, what can be used in studies in the future. So we want to determine an AI framework that works for mesophotics with all of the unique challenges that we're going to face. Examine the effectiveness of certain pre-processing steps, which I'll get into in a minute. And then see if the model that we can end up training is going to be accurate at estimating percent coral cover of images you feed into it. Our second objective is to examine the effects of geomorphology on a mesophotic coral cover. This is more to analyze that horizontal coral cover I was talking about earlier, and could, if we find things that are in the geomorphology that are indicative of coral cover, this could somewhere down the line potentially be used to predict where thriving mesophotic reefs are occurring. So to start with our study site, we have pretty much just the Greater Virgin Islands area, this area around Charlotte Amalie, and St. Croix. So before we get into actually running models on our sites, we have to train the model. And there's three things we're really looking at for the steps we want to analyze and what works for training an image identification model. The first is identification type. Then we have the model framework, the foundational model that we're going to build our specific model off of. And then the metrics we're using for actually training the model once we have all of our annotations and all of our pre-processing steps done. So starting with identification types, we have three that we're interested in potentially using. We have bounding box, polygon, and segmentation. So starting with bounding box, this is sort of the simplest type of identification that we can use. All it's pretty much taking is it's seeing the sort of item of interest in the image, finding the most left point of that item, the most right point of that item, and then the top and bottom, and drawing a box around it. So it's really simple, but it's really fast, and it doesn't require a lot of annotations. But it doesn't have the sort of fine-grained detail that we're going to see in something like a polygon, which is, instead of drawing a box around our coral, is going to try to essentially draw a perimeter. So because it's getting this more fine-grained detail, it's a little more complex, takes a little more processing power, and requires more annotations. And the final step in this is segmentation, which places a mask over each item of interest in your image, and is different from polygons in that instead of just drawing a perimeter, it's identifying pretty much every pixel in the mask, which lets you have a situation where if a coral has, let's say, the center of the coral dies from disease or stress or something, the mask can actually exclude that part of the coral, so you would just get all of the tissue around it. So that's a little more complex, requires more annotations, again, more processing power. The next thing we need to worry about is our identification framework. Again, what we're interested is these two types of detectors. There's tons and tons of frameworks out there, but these are the two foundational parts of those frameworks that we're going to be looking at. The first is two-stage detectors. These are more accurate and more complex, and what they're going to do is essentially break up the annotation process into two steps. The first step is detection. It's going to essentially do a bunch of proposals for where it thinks items of interest might be, narrow it down, and then go into the second stage, which is going to be that more fine-grained detail. If we were doing something like a polygon, it would be drawing the polygon around those items. Single stage detectors, however, are a little simpler. They run pretty much all those steps at once. They just look at the image and find the items of interest. Because they don't have this first step of narrowing it down, they're a little bit less accurate, but they are simpler to train and faster to run. So we decided for this project, since we have those problems with data availability, and since other projects in the Mesophotic zone will have those problems, we decided to go with the simplest possible model and see what we can make with it. So we went with a single stage detector, this YOLO V8. And we went with this because since it's had so many iterations, these 8 iterations, it's actually not that much less accurate than a traditional two-stage detector. So it's still pretty powerful. We went with a bounding box framework, and we'll get into the training metrics. So to train this model, I had to by hand annotate 1,500 annotations of Agaricea and Orbicella each. Because I had to train with so many annotations, I needed a large data set to train off of, because when you use an image for training, you can no longer run the model on it because you've already told it everything that's in the image. It already knows that image, basically. So we decided to go with the Territorial Coral Reef Monitoring Program. For those of you who don't know, this is a 20-year long data set of both shallow and mesophotic corals. So I took, I believe, 4 years worth of data off of the Territorial Coral Reef Monitoring Program to use as our training data. And then once we had all the annotations done, we moved on to the pre-processing steps, which we used blur, saturation, and brightness. So I've talked a lot about pre-processing, but I haven't explained what it is. Pre-processing is something you can do to your training set, to all of the images that you are going to input into the model, to help the model be a little bit more accurate and a little bit better at generalization. And what this is you're pretty much just augmenting these images before you put them into the model. So you can take the original image, and there's a bunch of things you can do. You can grayscale it, you can chop parts of it out, rotate it. But what I was interested in looking at was, can we actually simulate the changes that we would see in the light environment in depth with this pre-processing steps? So for our project, we decided to go with blur, color saturation, and brightness, blurring to simulate the differences in motion blur you would see from image to image, color saturation and brightness, both to try to simulate what we would see with changes with depth as it gets darker, as colors change in their saturation. And for each of these processing steps, we had low, medium, and high intensity alterations before we would put them into the model. So in total, I ended up training 26 separate image identification models. Each model takes about 4 hours to train. So this is over 100 hours of training time, basically. Oh, whoops, 1 second, we go back. And to show you guys sort of what this would look like, we have this image of a coral here. And when we would run the blur, color, saturation, and brightness changes, it would change from something like this to something a little bit more like this. So it's not a drastic change, but hopefully it's able to just simulate that enough to make the model better able to delineate between these different conditions. So once we've trained the model, it's going to output a few health metrics. The three that it's really going to output for us are precision, confidence, and recall. Precision is the fraction of correct annotations versus the actual annotations that the model should have gotten. So if we look at this graph here, if we say the blue side is all of the corals in the image, and this circle is all of the annotations that the model made, this is the precision. So it's the fraction of, oh, sorry, I got this mixed up. The precision is the fraction of correct annotations the model made versus the amount of annotations the model made. So it's going to be this circle of, these are all of the correct annotations it made. These are things that it annotated but was incorrect. So that's what precision is. Confidence is a metric that the AI is going to output itself for each annotation it makes, saying it is 60% confident that it's correct in this annotation, or 40% confident that it's correct in this annotation. And that will be used more for locking our final model at certain confidence thresholds to basically tailor our model to what we want it to be better at. Recall is what I was talking about earlier, where it is the amount of total annotations it should have gotten versus the amount of annotations it actually got. So these are going to be the three metrics, and they're going to output basically 4 graphs for us. The first graph is this precision recall graph. This is just a random one from one of the models that I trained. And what this is looking at is the precision of the annotations when locking it to recall a certain proportion of the corals in the image. So If we wanted it to recall 100% of the corals, it's going to be less accurate because it's just going to be throwing annotations around everywhere. But if we wanted it to be 100% precise with all of its annotations, it's not going to get as many of the corals, right? So this is going to be a big metric for how healthy our model is, and we're looking for a precision recall value here of about 0.75. The recall confidence curve is similar, but instead of precision, we're looking at the confidence of the model in its annotations. So say we wanted to lock the confidence at 0.6 or about 60% confident. How many of the corals is it recalling? It's recalling in this one about 60% of the corals. So this will be useful along with the precision confidence graph to help us delineate where we want that confidence threshold. Precision confidence is similar as well. If you lock the confidence at certain thresholds, how precise is the model annotating? The last health metric that we're going to be looking at is this confusion matrix. Basically, what this is saying is what are the correct annotations on the bottom and what did the model predict? So in this model, if it predicted Agaricia, about 65% about 65% of the time, it was actually an Agaricia. If it predicted an Orbicella, about 90% of the time, it was actually an Orbicella. So once we have a working model that we're happy with, we need to make sure it's accurately estimating coral cover if we want to deploy it on these big data sets. So how do we go about doing that? I decided to start by putting a 10 by 10 grid on 100 images across all of our data sets that we're going to use. So this puts 100 boxes on each of the image, and I would go through by hand and identify essentially each box. So I would say this is an Orbicella, this is just background, and this would give me a rough percent cover from each image. I can then run the model on those images, and it outputs something like this, where it's going to put all of these boxes around all of the corals. I can then take the dimensions of each of those boxes, calculate their areas, sum all those together, and get a percent cover for the image. And then all that's left is to compare the area in the bounding box versus this control that I made. So those are all of our steps. On to the results of what we found doing all of this model training. First off, we can talk about the pre-processing, the changing saturation, brightness, and blur. Across the 26 models that I was able to make, the average precision recall and average confidence was just under that 0.75 mark we're looking for, with the precision recall being at 0.72 and the confidence at 0.71. But if we look at the no pre-processing steps, those numbers actually go up a little bit, which is interesting. Having the precision recall just at that 0.75 threshold we're looking at, and having the confidence matrix above that at 0.82. While this is interesting that it has a higher accuracy, there is a caveat to this in that if you remember me talking about the pre-processing steps earlier, they're mostly for generalization. So this model, while it's more accurate on the training data that it's already seen, it might be a little bit worse at generalizing between those environmental conditions. However, our best model did have pre-processing steps. It was a low-level saturation increase and decrease, increasing it and decreasing it by 25%. No brightness alterations, and then a blur with a kernel of 6. And that left the precision recall value at 0.81 and the confidence matrix value at 0.87. So we have our best model, but we want to look a little bit more into how these specific pre-processing steps affect the accuracy. And I didn't, unfortunately, have enough models to test interaction effects, so these are just all tested in a vacuum. So looking at saturation by itself, we see no real significance between any of our different levels of intensity for saturation changes. Looking at brightness, we see the same thing, no real statistical significance. Blurring was a little interesting. Um, the high levels of blurring the images ended up having significantly lower confidence matrix values than low level blurring and no blurring. This could possibly be due to when you are testing the model against itself, it's testing on some of those augmented images. So trying to identify really blurry images might be difficult for the model to test against itself. So that might be why we're seeing this lower value here. So now that we have all of the pre-processing done, we can actually look at the health of this model. Starting with the precision recall curve, we see that all classes at 0.812 at that threshold that we saw earlier. But we see that Agaricia ended up being much lower on this graph than Orbicella. And looking across all of the models, this was a relationship that stayed consistent across every single model that I made. Agaricia always was harder for the model to identify than Orbicella. There's a couple possible reasons for this. I think the most likely is that Orbicella at depth has a lot more of unified morphology. Orbicella is really that genus that you can't identify species to species just based on images. Agaricia has a little bit more changes from species to species, a little bit more morphological diversity, which makes it so that the model has to be able to annotate a wider variety of images and makes it a little bit harder for it to do that. Confusion matrix ended up with a 0.92 on Orbicella and a 0.82 on Agaricia, so that all looked fairly good. And then looking at the recall confidence curve and the precision confidence curve to try to narrow down what we want that confidence threshold to be in our final model, I ended up noticing these 2 points, which was a confidence of 60% on both of the images. If you use that on the recall graph, it goes up, and then at about 0.8. So if we locked confidence to 60%, we're recalling about 80% of the corals in the image. And we're doing that, if we follow this line, at just under 80% accuracy. So I decided to go with a 60% confidence interval for a 60% confidence threshold for the actual deployment of the model. So now that we've talked about our final model, we can actually test if it's accurately predicting coral cover. Looking at Orbicella first, what we're looking for in these graphs is basically a slope of 1, an intercept of 0, and an R-squared that explains the majority of the variation. Because this is the control that I estimated from my technique versus what was estimated by the model. And what we see in Orbicella is actually a pretty accurate model to what we wanted. So we have that intercept at about 0 and a slope of pretty much 1, with an R-squared explaining about 85% of the variation in this data. However, where we run into a problem is with Agaricia. So the intercept is a little bit above 0, and we have this 1.3 slope with the R-squared only explaining about 54% of the data. But looking at this graph, I noticed these points. You can't really tell, but these are 4 different data points that had identified high levels of Agaricia cover in the model where there was no Agaricia cover at all. So I decided to look into those, and I ran into pretty much with each one of these a situation like this, where we have no coral cover here. This is all just sand, and some sort of foreign object in the photo. In this case, a drop camera rope. In a couple of the cases, they were measuring tapes or things like that. And it seems like these man-made objects are for some reason throwing the model off a little bit. So what I decided to do was I set a threshold for unusual high levels of Agaricea cover. I set it at about 14. And I would go through, in the final model, when we actually deploy this, I will go through each of the images that it identifies at a higher level than that 14% and make sure it's not running into a situation like this, basically. So when we do that here and get rid of these 4 data points, it ends up being a lot more accurate. It still has that slope overestimating Agaricea cover in general, but the R squared ends up explaining 80% of the data. And as long as we're essentially comparing it against itself, I don't think the slope being that different is going to cause that much variation in our final data. Here's the graphs of combined Agaricea and Orbicella cover. You can see actually that changing those few points in Agaricea didn't really change the overall graph that much. But we're still going to want to do that when we are analyzing Agaricea and Orbicella separately. All right, so that was a lot of information. That's a lot of AI stuff to throw at you guys right away. So just to summarize everything I've talked about thus far, our model exceeded the 0.75 precision recall threshold, as well as the confidence matrix threshold for a healthy model. Our best model had low levels of saturation and blur pre-processing steps, but the individual pre-processing steps had little to no noticeable impact on the model health when examined in a vacuum. Our final model had estimates coral cover at a slope of 1.13 and an R squared of 0.85. So it seems to be fairly accurate at identifying coral cover. So now that we have this, now that we've gone through all this and have our final model, we can actually deploy it. I took 7 data sets of mesophotic imagery, the territorial coral reef monitoring program, the deep coral reef monitoring program, which ended up being my 2 most abundant, and then Panda, Deep Lion, No Dice, CSAP, and Buck Island. Just to summarize, most of those are coral surveys. One of them is a lobster survey that they just happened to have benthic imagery, so we still decided to run our model on that. And that leaves us with 5,716 images of the benthos that we got to run this AI model on. So the geomorphology that we're interested in to hopefully be able to figure out what constitutes good habitat for corals is depth, slope, that derivative of slope or the slope of the slope, aspect, which again is the direction that the slope is facing, north, south, east, or west, distance from land, and then location, either north of St. Thomas, south of St. Thomas, north of St. Croix, or unfortunately, south of St. Croix only had a single data point, so we ended up not being able to use that. The statistics I ran was the continuous variables, depth, slope, slope of slope, distance from land, were all analyzed using a generalized linear model. Aspect was converted into its north, south, east, west categories and analyzed using a Kruskal-Wallis, and location based on these categories here was analyzed using a Kruskal-Wallis. Starting with this very ugly PCA, what we were trying to do here was essentially get all of the geomorphological points and group them by high, low, and medium coral cover. And what we were hoping to see would be delineations in essentially separating these groups, essentially seeing that there's high coral cover in one part of the graph, low coral cover in another, and medium in another. But what we see is kind of this mishmash, which doesn't really bode well for the geomorphological impacts. So we decided to look at them. Looking at this data, we have our combined Agaricea and Orbicella cover, Orbicella and Agaricea separated, and then the four geomorphological characteristics we were interested in. There's a few things I want to talk about with this graph. The main one being that while it looks like we have potential bell curves or things like this, there was no statistical significance found in this graph, in any of these graphs. And that's primarily because what you can't see here is about 90% of our data points are at the 0 to 1% coral cover range. So they're really heavily weighing these graphs. And because a lot of these 0 to 1% coral cover estimates were from coral cover surveys, I didn't really feel comfortable removing them from the equation here. Other things that are important to note, especially with this potential bell curve with depth, is that this 30 to 45-ish meter range is also where we have the vast majority of our images. So it's hard to say if this bell curve we see is a bell curve of coral cover having really high peaks at these depths, or if this is a really high peak of just lots and lots of data that's going to eventually have some of its spots at high coral cover. We have a similar relationship with distance from land. Most of our points are T crimp and D crimp, which are along the shelf edge, which falls solidly into this sort of range. What we don't have this sort of problem with is this slope graph. While it's not statistically significant, it also doesn't have any of those compounding factors that's biasing it towards any sort of slope having a really high level of coral cover. And so there's potentially, at least with the highest possible points, some sort of relationship here. But with the data that we have, there's not really any conclusions we can draw here. It just, slope is potentially an area that should receive more study in the future. The last thing I want to mention is you probably have already noticed that the combined graphs and the Orbicella graphs look very similar across pretty much all of these. So Orbicella, it appears, tended to be the main driving force of overall coral cover in the Mesophotic zone across all of our sets. Moving on to the location graphs. We found that the reefs south of St. Thomas tended to have higher coral cover than those north of St. Thomas and north of St. Croix. We expected this with St. Thomas North, as we said before. They've already been observed to have lower coral cover north of St. Thomas, possibly due to that increased wave energy. But what surprised me was St. Croix North having such low coral cover, because we also had several sites there along the other side of the Puerto Rican shelf edge, which I expected to have a similar relationship to coral cover as the Puerto Rican shelf edge south of St. Thomas, but that's not what we ended up viewing. So what characteristics are going on here to cause this low coral cover? We're not really sure. It could be a million possible things. I mean, the shelf edge here is a lot closer to land, so there's potential sedimentation. Potentially, maybe St. Croix North has more wave energy. There's just no real conclusions we can draw from this, but this definitely is something that could be interesting to look further into. Looking at aspect and percent coral cover, we have a couple things that I wanted to point out here. Most of the sites were not significantly different from each other, but reefs slopes heading northwards were significantly lower than southwest facing slopes. And I think this is probably just driven by the fact that those reefs north of St. Thomas and St. Croix were so low, had that really low coral cover. And since they are north of land, they're in general sloping away from the nearest landmass. And so a lot of their sites are sloping northwards. The other thing that I wanted to mention that I usually wouldn't if this wasn't backed up by literature is this relationship of southwest facing slopes maybe being a little bit higher coral cover than southeast facing slopes. The majority of these data points would again be along the shelf edge with T crimp and D crimp. And this backs up findings by Sherman et al. 2010, who observed that southeast facing slopes had lower coral cover than southwest facing slopes, potentially due to interactions with sedimentation or the intensity of the slope. So that is another area that could look into a little more research potentially. So to summarize everything we've talked about so far, the simplistic image identification model that I made accurately was predicting coral cover. So moving forward, that might be something that's applicable to other mesophotic studies. Pre-processing augmentation did give us our best model, but really narrowing it down to what are going to be the best pre-processing steps for mesophotic corals also requires a lot more study. The geomorphological effects had a lot less impact on coral cover than I had expected going into this project. Previous studies had found that they're pretty impactful on coral cover and community composition. And there's a few reasons for this. This may be simple variation from the fact that I am using 7 different data sets or that impact of low coral cover. All right, so to conclude everything, due to limited training data, continuing to use these simplistic AI models might be more applicable for mesophotic studies so that we don't use all of our available imagery in training a model. Emulating changes in the environmental condition seems like it could be effective moving forward, but a lot more research needs to go into this sort of area, looking at what environmental conditions can we simulate, what are actually helping, and does simulating environmental changes with pre-processing steps, is that significantly better than just using more typical pre-processing steps like doing grayscale or those sorts of things? Geomorphological impacts had less impact than previously anticipated. Another possible reason for this is that, like I said earlier, previous literature really focused on that really complex shelf edge, and that geomorphological complexity that we saw there isn't really seen across the rest of the Mesophotic zone around St. Thomas. And so those geomorphological impacts might be impacting coral cover when they're seen at that level. But across the rest of the Mesophotic zone, it's possible that they're not really impacting coral distributions as much. However, this comes with the caveat of we used several different data sets, a lot with different sampling techniques and intents behind them. So there is a potential variability added by those data sets. And this requires a lot more study to really draw definitive conclusions about. So here's my literature cited. And I would love to acknowledge my committee for all of their help along this process. A big thank you to all of our partners at the Queensland University of Technology, particularly Dr. Dorian Tsai, Matt Dunbabin, and Serena Mao, for taking me in when I had pretty much zero experience doing this sort of coding work and teaching me to the point where I can now code these neural network image identification models. They've been incredibly helpful in that. Thank you to Travis Hanlon for all the help with the Ranger bots, and Aaron Rapp for helping with setting up the computers that we ended up training the models on. Thank you to Dr. Jeremiah Blondeau for helping out with all of my ArcGIS work. And extremely special thank you to Alex for helping me in every step of this process, being so supportive and so amazing. I don't know if I'd be here without her. And that goes to all of my amazing family and friends who also helped me along this whole process. You guys have been amazing. And finally, thank you to Point Blue Conservation Science and the NSF STEM project for giving me the funding to do this. So, with that, any questions?
Okay, great. Thanks, Zach. I think I'm on. Yeah, I'm not muted. Yeah, so any questions in the room? And then we can also, if anyone has any questions online, feel free to put them in the chat or raise your hand.
Zach, great talk. Exciting
Thank you.
My question is related to the previous studies that you're kind of comparing your results to. What kind of sample sizes were they using in terms of like finding differences in the aspect and things like that? Like you had a huge number of images that you were looking at, and I'm wondering, you know, is it potential that they just saw differences because they just had this small sample size where that just randomly happened?
Yeah, in general, a lot of these have, because of the data analysis techniques I talked about earlier, have smaller sample sizes. A big one that I was using was Sherman et al. 2010. That was for that difference in southwest and southeast facing slopes. That study was looking more at the geomorphology of the shelf edge and what that actually looks like, and the actual coral cover in those two slopes was more of an observational part of that study. So this is what I'm talking about when I'm saying that there's a lot less research out there for the horizontal distributions, because there weren't really that many studies really looking into that sort of thing.
Hey, nice presentation. Amazing amount of manual annotations. I'm glad to see.
Thank you.
I was interested to wonder whether you did any color augmentation. I know at the Mesophotic, especially, that's going to be a big issue with the imagery. And yeah, just wondering if you looked at that.
Yeah, so I mean, like I alluded to at the end, I'm pretty new to this whole Python coding, doing all of that sort of stuff. So the sort of color shifts with depth, I tried to use the saturation to simulate that a little bit because it would change those color saturations. But actually changing the specific values, the like RGB values, I wasn't really able to figure out in time for this project. Yeah, Pim.
Hey, Zach. Great presentation. Really done a great job and really well explained, especially, giving all those model health metrics, because they're not always that intuitive when you see those graphs at first sight. So I really enjoyed that. I had two questions. One was more regarding, I was just wondering how you kind of divided the data set into, your training sets versus the validation versus the actual test set, like the three components. And then, well, maybe I'll let you answer and then I'll ask you the other question.
No, for sure. So I didn't explain this in my presentation. So to everyone who's not familiar with AI stuff, you have three sets of data when you are plugging your images into the model. There's a training, a test, and a validation set. The training set is going to be all of the images the model is going to be basically learning off of. And then it will make, after it does like a round of learning, it'll make a bunch of guesses on the validation set to see what it's doing right, what it's doing wrong. Then it will go back through the training and validation sets over and over again. And then the test set is something that the model never sees, and that's where all of the health metrics came from. So the model doesn't know what those corals look like, and it's testing itself. Looking at a lot of literature, I sort of settled on an 80%, an 80-10-10 split, with 80% of it being the training data, 10% validation, 10% test. And I pretty much just had it randomly pick those images among all of the training set that we had available.
Awesome. Yeah,
Yeah.
and pretty exciting to see that you got this working. Like, I think this is going to be increasingly, important with a lot of like monitoring programs to be able to automate it. And what's particularly neat to see is the bounding boxes approach as well. So it's not just, point annotations and what it is, but also getting an idea of size and core cover. What I was wondering about, so you mentioned with the different data sets, that they obviously were collected for different purposes, and that was kind of part of the challenge, and potentially maybe obscuring some of those links with geomorphology or geography. I was wondering to what extent, those data sets represent different time points, and if there's anything going on there as well that maybe that's obscuring geographic patterns, or.
Yes, that's definitely another potential compounding factor in all of this. I mean, T-crimp and D-crimp alone both go across several years. And one of the things I didn't mention with those as well is there's a lot of sites that share the same latitude and longitude. So there's a lot of images that when they did share lat long, I pretty much just had to average those to avoid that sort of pseudo replication problem with those consistent data sets across years. But yeah, the short answer is yeah, there's probably some variation added to it across the years, because T-crimp, I think I ended up using 5 years of T-crimp in the actual data I deployed on, and something similar in D-crimp. And then all those different data sets, the smaller ones that I used, were taken at different time points as well. So there's potentially something on there.
Yeah, it makes sense. But we really need to see now to actually, get the metrics for the different time points at those different sites and see how they compare with the published data, right, from these monitoring data sets.
For sure.
Yeah. Awesome. But well done. Yeah. Thank you.
you.
That was it.
That's great. Thanks, Pim. And also, we will have a chance in private committee after this round of questions too, to ask more questions, more thorough questions. Anyone else? I have one question in front of everyone. I think would be interesting. So now you have this model, and assuming that it's doing pretty well, it looks like it's doing pretty decent. If you could go out and collect a dream data set that tested it, what would you collect?
I mean, this is all in that vein of compounding like variability. I think in an ideal world, if we could take the Ranger bots or the AUVs out and collect a bunch of essentially points around St. Thomas in areas that are not as much shelf edge, in those areas where there might be less geomorphological complexity, I think that's really interesting to look at in terms of being able to move this forward into something like a predictive model, to be able to get that more fine-tuned understanding of geomorphology and its impacts, I think is probably where you go. So long story short, probably take those ROVs and those better sampling techniques and just put them in as many interesting areas as we can around St. Thomas.
All right, great. All right, well, thanks everyone for coming and staying so late. I know you guys... Is someone online? Question?
I got a question.
Oh, okay, go for it.
Okay, so now that you kind of brought this up, I'm just going to say that we have a massive data set from the last 3 years around St. John of random stuff with GPS associated with it because we pull a GPS for all of our dives. So I was wondering that if using the GPS, you could find the locations of everything, and then using LiDAR, you can kind of quantify slopes, right? Would that help you guys with furthering your work? Because I want to figure out ways to use the data we have.
Yeah, I mean, absolutely. What I mean, the whole idea behind all the different data sets we used was I was in a meeting with Tyler and we had the model done, we had it ready, and we we're like, okay, what do we do? And we pretty much grabbed every Mesophotic data set that we could find that we thought the model would be applicable for, and just ran the model through it. So any extra data, anything else that could help us flesh out those relationships would be really easy to run the model on. I mean, at this point, it's at a point where you can pretty much hit a button and it'll run for an hour and annotate all the images.
Yeah. Well, Mariah, that's a shallow water data set, but that would be kind of an interesting outgroup to just run the model on at no cost.
Just see what happens. Yeah, I think it'd be
Yeah,
cool
see what
too.
happens. Awesome.
Cool. All right. Thanks, everybody. All right. If the committee, if you guys stick around, we'll retire to the privacy in about less than 5 minutes.
Congrats, Zach. You did great.
Thank you.
Oh, sure. Oh, thank you. I have to go get my backpack. Yeah. You need help.